Right, a particularly common part B question revolving around differentiation is determining whether a function is strictly increasing or decreasing. So basically it leads on quite nicely from what we were doing in terms of the nature tables, and you can use that to help you here. But the idea is we're looking for specifically where a graph is going up or going down, depending on the question. Okay, so we're interested in the shape of the graph, more importantly, the gradient of the graph. In which case, as I say, you need to actually differentiate to find this, okay? So you'd be given a function, and we take that function, differentiate it, and then you're just looking for the gradient, right? There's three different types of questions around this. I'm going to go through all the different examples. They're not too difficult. There's only really one instance, which is in the third example, which you need to look out for and be careful of, and it links in to what we're doing, the work we're doing on range and domain, okay? But there's three kind of outcomes that we're looking for. We're either trying to find these outcomes or we're told about these outcomes, but either way it revolves around these three facts, okay? So when the derivative of the function and with a value a is greater than 0, the whole function is strictly increasing at that point, okay? So where x is a, the function is strictly increasing. So vice versa, if the derivative with a value a subbed in is less than 0, then the overall function is decreasing at that point. And then as we already know, when the function with an a substituted in, when just a number substituted, when it equals 0, then the function is stationary, okay? So this is very, very similar to what we're doing in terms of the nature table, but the question you asked in the first instant is slightly different. Okay, so I'll go through three examples. There's ever so slight difference between all of them, but they're not too long, not too stressful. Okay, so the function f in this case is defined by f of x equals x cubed minus 5x plus 6. Show that f of x is increasing when x equals 2. So nothing about differentiation in here. Okay, but we're trying to find when the function is increasing. So what that basically means is when is the graph going up? So from left to right, when is it actually going up? In other words, when is the gradient positive? So if we're trying to find something or trying to establish something about the gradient, then obviously we're going to need to differentiate. And we want to find out, we want to show that it's particularly increasing at a certain point. So once we've differentiated, we're just going to substitute in this point, okay? So differentiate first of all, so f of x is x cubed minus 5x plus 6. So that's in differentiable form, so we can just go straight ahead and differentiate, giving us 3x squared minus 5, okay? So we want to show that it's increasing at the specific point, so we're going to take that specific point, 2, and we're going to substitute it in. So f dash 2 equals 3 times by 2 squared minus 5. So x is replaced by 2's, and we just work that out as 7. Right, 7 in by itself doesn't really tell us an awful lot, okay? What it actually tells us is the gradient. But more importantly, it's the fact that the gradient is positive. And if the gradient is positive, then the graph is increasing, in which case the function is increasing at this point, okay? So we just need to make that clear in terms of our answer. So f dash 2, so in other words, when 2 is substituted into the derivative, it is greater than 0, and therefore f of x is increasing when x is 2. Right, this first line here, my line's kind of moved a little bit, but it should basically be that f dash 2 is greater than 0. So that bit must be stated. Okay, so you have to do that obviously to get the answer. And you know the SQA from kind of other topics are quite pernickety about these kind of things. So you have to put that line in, okay, and you have to obviously answer the question. So because it's greater than 0, it is increasing, okay? So a similar kind of example, but this time we're trying to find the range of values for which it is increasing. So in the previous one, you were told, you were given a point and you had to show that it was increasing. So this is kind of the opposite of that. We're trying to find the points at which it is actually increasing. So without knowing those points in advance. But the same kind of start to this question, we want to take this and differentiate it. That is not differentiable form, right? I think a few of you at this stage, you're kind of looking at the fact that it's brackets and just automatically assuming you can do it with a chain rule. But that only really applies when you've got the single bracket and a power. Okay, so just look out for this. The best way of doing this, I mean, the idea is if it had power of 5, you could multiply it out. There's just a shortcut using the chain rule. But for this one, it's obviously much easier to multiply out and putting it into differentiable form. So just remember what I said. We've not differentiated this stage, so we're not writing h dash x. We're just writing that h of x is the same in both of these lines, okay? But now we're at a stage where we can differentiate, so we can write h dash x, and that will equal 4x cubed minus 32. Right. What we want is we want the range of values of x for which it is increasing, okay? So I want the derivative to be positive, okay? So I want to know the values when the derivative is positive. In other words, I want the derivative to be greater than 0, okay? So 4x cubed minus 32 is greater than 0. So what this gives us is an inequality, and there's certain things we have to just think about when we're dealing with an inequality. It's not necessarily going to come up in this one, but in the next example it does. Okay, so we can solve this as it is. Because it's x cubed, okay, we're only going to get one answer here, so we can move the 32 to the other side, and then we can divide by 4, and if x cubed is greater than 8, then we're going to find a cubed root of both sides, in which case x is greater than 2. Okay, the question made it clear enough for us to leave our answer like that. So find the range of values of x for which h of x is increasing. X needs to be greater than 2. Okay, so it's fine to leave it like that. And that's pretty much it for that question. Okay, so the last one is a bit more complicated. Okay, so we've just got another function again, but we're going to find the range of values of x for which p of x is decreasing. Right, on the surface it's exactly the same as the last question. We've got a function. We're finding decreasing this time, so there's only one slight change. It just means that when we've found a derivative, we're going to make it less than 0. We want it to be less than 0. But when you get further through this, there's just one thing I need to point out. Okay, so start by differentiating. That's in differentiable form. So p of x equals that, in which case p dash x is going to equal 3x squared minus 6x minus 9. So then related to the question, we're trying to find a range of values of x for which p of x is decreasing. Okay, so we want this to be less than 0. Okay, because there's an x squared, we're going to factorize, and I think I've done this one in 2 stages. So you've got 3 as a common factor, and there'd be x squared minus 2x minus 3 left in the brackets, which is a trinomial, which we can factorize to give us this. Okay, so if you're writing up your notes, you can write an extra line in here. But that is it fully factorized. Right, the 3 plays no part in this, so you can actually divide both sides by 3, but I haven't here. But the temptation, I think, at this stage is because obviously if it was equal to 0, if you had 3 bracket x minus 3x plus 1 equal to 0, what you'd then do is you'd write x minus 3 equals 0, x plus 1 equals 0, and solve it. So the temptation here is to do x minus 3 is less than 0, x plus 1 is less than 0. But it doesn't make the same. You can't do that for an inequality. Okay, so you have to take a slightly different approach here and basically think about the graph. Okay, so you could use a nature table, but because of the way the graph is, because it's just a quadratic, just an x squared, it's straightforward enough to just think about the actual the curve and what it looks like. So what we know from this stage, so don't worry about the fact that it's less than 0 just yet. This is still the graph, but it's the graph of the derivative. And don't get confused here. We're not drawing the graph of this. We're drawing the graph of the derivative. So we're drawing the graph of the x values that show us the kind of the gradient of the different points along the original graph. And I know that's a little bit strange to get your head around, okay, but just bear with me a second. So we've got x minus 3 and x plus 1. They are our roots. So in the same way as always, it basically gives us the points at which it crosses the x-axis. So minus 1, 0, and 3, 0. So then we're thinking about the shape of this, right? It's a quadratic, so we know it's going to be a smiley face or a frowny face, and it's the fact that x squared is positive means that it is a smiley face, okay? So we can kind of fill that in. It's going to look something like that. We're not really interested in the turning point. Don't worry about that at this stage. What we're looking for is we're looking for this graph and where it is less than 0, okay? So remember, this is the graph of the derivative. This is basically showing us the gradients at different points. So what this means, okay, and basically what happens here is that the y-axis is telling us about our gradient. So our gradient, when it's above the x-axis, is positive. In other words, it's increasing. So here and here, it is positive, in which case the gradient is increasing. But we're looking for where it's decreasing. So in all of these values, okay, the gradient is decreasing. Okay, and in terms of, we can't just write it like that, we have to actually write it in a mathematical way, right? You could write this out as a sentence. So what we're saying is basically when x is between minus 1 and 3, the graph of p of x, or the function p of x, is strictly decreasing. Okay, but in terms of shorthand, or the best way of writing it, we can write it like this. P of x is decreasing when x is between minus 1 and 3. In other words, when x is greater than minus 1, however, less than 3. You have to write it all in one stage if you're going to write like that. As I say, you can write it as a sentence if you're more comfortable doing it that, but this is obviously the shorthand, quick version of doing it. But just bear in mind, this is not the graph of the original one. Okay, a cubic would look like a kind of S function, but this is the graph of the derivative. This is the graph basically showing us what's happening with the gradient. So here the gradient is positive, and here the gradient is positive, but here the gradient is negative, in which case it's strictly decreasing between minus 1 and 3. So if the question was flipped and it asked you to find a range of values of x for which p of x is increasing, it would be where x is less than minus 1 and where x is greater than 3. Okay, but the bottom line is, when you have a situation like this, don't just do it in the same way as you would if you're solving an equation. It's slightly different, in which case you have to think about the graph. Okay.